Good afternoon. We are going to get started. So we're here to talk to you about advancing technologies in the 3D design world, and I had so many troubles here with my 2D projection, but hopefully the rest will go smoothly. I'm going to start out, before introducing our panel today, with a small clip, a video, an animation. As I realize in this room, there's probably a varying range of experience with some of the things that we're going to talk about. So we will not only try to cover it in a basic realm and introduce 3D printing to those of you that are brand new and fresh to this topic, but we'll also try to go much deeper with our expertise here on the panel and go into some of the subject matter on a deeper level. So to start, in the entry point and in the wider perspective, it's in Catalan, but text is not important.
Happy birthday, son.
Happy birthday, son.
Glass cup design.
Yeah.
Download. Share. Uploading. Save to disk.
Share, transfer in data.
Analyze. Share, transferring data.
Materials.
Masih dulu kira.
Who's new?
Okay, so I promise we will talk about medical topics as related to 3D printing. But I think it's important to open with that wide perspective to see it's not just what's coming out of the printer and the machines, but as our first panel is here to represent, it has a lot to do with these wider topics. Distributed design, how technology changes design, community-based, networked design. So I will start with introducing myself, the moderator. I have an architecture background, and I'm director of Live Architecture Network. We do a lot of technology workshops. Keep it brief on me and more so on the panelists here. So our first is Darrell Hurt. He's the section head of NIH, the 3D Print Exchange, which has newly opened online print library. I will, as I introduce you now, have each one talk for one minute, let's say, more in depth about their experience and present endeavors.
Thanks. So my experience is as a crystallographer, someone who's taking very complicated 3D pictures of proteins and macromolecules inside of cells and trying to communicate these complicated three-dimensional shapes to other researchers who are maybe not so good at visualizing on the screen these 3D shapes. So we actually created a way to print them out so that people could better understand what it is that I'm trying to communicate. And then beyond that, we've expanded into all kinds of microscopy, and then any kind of image data that could be in 3D. So our website that we just launched is a way to upload that 3D data that you all have some experience manipulating, whether it be molecular microscopy or medical imaging, or perhaps also even some gadgets that you designed for the lab. And the website allows you to upload and share those or download those from other people and even create your own using the tools on the website. So that's what brought me here. That's why I'm excited to be here and very honored actually to participate.
Okay. Next for my titles, if we could move over to Scott. Scott Summit. He's the Director of Technology of Bespoke Products at 3D Systems. You want to introduce further?
So my background, I'm an industrial designer, and so that's half fine art and half engineering and problem solving. Started a company a while back called Bespoke Innovations, and it was looking at the idea that you might be able to 3D print prosthetic limbs for people throughout the world in a scripted way so that you can get around the limitations of the lack of doctors and their distribution around the world. That company is now acquired by 3D Systems, which is the big player in the 3D printing world, and I'm now the design director of that company, and we look at everything from 3D printing in space to 3D printing food to 3D printing all kinds of body corrective systems, 3D printing musical instruments, crazy stuff with will.i.am, you name it. We are looking at how 3D printing is going to connect into our lives in every way. And medical is actually a very big sweet spot for 3D printing for all the obvious reasons. So that's really where we focus a lot of our attention.
And back to Kayla. Kayla is the San Francisco mayor of 3D Hubs.
Oh, it's my turn. Yeah, so I have no background in engineering, designing. I'm just like all you folks. My background is more in social responsibility work. And back home in the East Coast, we have a foundation called the Gasoline Alley Foundation, where we teach inner city youth, adults with low income, to create businesses that are socially responsible and that will give back to their local community. So I came out here to the West Coast to learn more about 3D printing. And then I researched, tons of research, and I found 3D Hubs. They're based in Amsterdam. Basically, what 3D Hubs is all about is they connect people who want to make a 3D print with people who have printers. And you just walk down the street to your neighbor's house that has a printer, and you pick up your design. It's really easy. I've been using it. It's fabulous. And we have a large range, a variety of materials, printers that we have on board. And yeah, that's it.
Okay. And Jon Schull at the end of our panel. He's the founder of Enable.
I'm Jon Schull, the founder of Enable. Enable is an online community of volunteers who are using 3D technology to design and to fabricate and to fit and to deliver 3D printable prosthetic hands and arms and soon other parts, which have been compared favorably to commercial prosthetics, which cost, I kid you not, $40,000 or so, and we're giving ours away for free.
Nice. Okay, I think we'll start there at the end, or on this topic, as Jon has introduced some of his work, this idea of what it means to 3D print in a sort of network fashion, right? So we're all in the information age of where we can now promote that information can travel globally and products don't necessarily need to, right? So we have this community of printers. Could we speak about how, on one hand, there's this range now of talent from amateurs that are starting to use equipment that's more accessible, and we'll get into thereafter kind of the more professional range of 3D printing. Jon and Kayla?
That would,
You can
okay.
start that.
Right. So, you'll see that Scott, for example, is a real professional, and I am a serious amateur, and my community consists of everything from 13-year-old kids who are getting hands and learning how to do 3D printing up to serious professionals. And one of the interesting things is that in an online community like this, you can take people with a diversity of technical skills and people skills. And just to give you an example, I have made a couple of little videos which I share with the community, in which I say, you could do something sort of like this, and other people in the community will look at those videos, and 2 days later, I'm seeing 3D models and 3D printed prototypes of this kind of thing. So it's really creating a whole new opportunity for new kinds of designs and new kinds of design processes.
Yeah, and to add on to that, it's also it's changing the prototype conversation. You create one thing and you're like, oh, I don't really like it. I don't like the color. It's too small. It has some spike here. I don't like it. That day you can change it on your computer and then pick it up. It can be a 0-day delivery time or whatever. That's using 3D hubs, of course. The turnaround from designing the artwork. Or the design, the print, and putting it onto the 3D hubs, picking a hub. It's a 1.2-day delivery time. So that's all it takes. So if you want to change a prototype, you can pick it up the next day instead of waiting weeks for it to come back to you. So it definitely changes the conversation, and yeah. Yeah.
So I'm a federal government employee, and you might be wondering, what is the government doing in this? Well, one of the reasons is the president's agenda for manufacturing 2.0. So the idea is that this kind of 3D printing is relatively simple. If you have the printer, operating the printer, depending, can be relatively simple. So what this means is that for people in developing countries or people with not a lot of education can actually get in on high-tech manufacturing with very little training. It also means that the design elements of 3D printing is more complicated, and so it begs, what should our education look like so that we can use this more effectively?
So I want to go back to those that are still trying to wrap their brains around it. What exactly technically is 3D printing? So maybe we could have someone start off with really talking about what is that process. We saw a little bit, I think that's the clearest, simplest animation I could find you of just layer by layer we're additively building, but I open it up to maybe a further description and starting to talk about the range of machines from the ones we saw here today that are being demoed for very affordable rates to there on up.
Yeah, so that is the big challenge, that people keep thinking that's going to consolidate into one printer that can do everything, and it's anything but. If anything, it's broadening out more. The machines run from a consumer level machine, which will run you around $1,000, to the professional machines, which are which can go up from there. They'll run from $20,000 up to $1 million, and you get what you pay for all along the line. To the fancier machines, which are actually multi-million-dollar machines. These are industrial equipment. What I mean by you get what you pay for is you really want to find the attributes that you're looking for, and there will be a machine that will meet those attributes. So if you want to print sugar, yeah, there's a machine for it. Ceramic, titanium. If you need something very, very strong, like the Scoliosis Brace here, that is an $800,000 machine. You can't get away with that for anything less than $800K. Then again, these other machines, the green parts here, those are done on a $1,000 machine. So they don't have the same mechanical characteristics, the same strength, the same durability, all the things that a medical product would require or an aerospace. But at the same time, you don't have to, you save $799,000 in the process. So on the flip side of that, though, it's kind of like photocopiers, that you don't have to own the machine anymore, that there are cloud services that will cover it. So if you want to, if anyone in this room wants to print something out of titanium, gold, ceramic, glass, elastomer, polymer, you name it, you have the exact same access to this equipment as I do, because you can simply upload it to the cloud. It will come in a box a couple days later. So it's been democratized in that sense, where if you want to have a machine, you can buy a machine and you can name your price of what you want it for. But if you don't want to actually buy a machine, every bit of functionality is available to you, just as if you did.
Yeah, I know it. I know I'm agreeing with everything that he's saying because I'm so passionate about it. And it is. It's just like there is endless amounts of opportunity with this whole field. And you can be a beginner or an inexperienced. You can be a hobbyist. You can do a DIY, doctor, engineer, mechanic. I mean, it's just a long list of occupations that will benefit from this industry.
And actually, to build on that, one of the things we were talking about a little earlier is that schools are trying to get their heads around this because they don't know which lab to put it in. Do they put it in the machine shop? Well, they could, but it also kind of belongs in the fine art department because it's a fine art tool as much as it's an engineering tool. I work with the guys up the hill here at CARMA, the Center for Music and Acoustics Research. We're 3D printing acoustic guitars. They're also printing the throats of different throats to see the acoustic properties that a throat makes. So there are history, archaeology, anthropology, architecture. Every field is embracing it in their own way. So it doesn't really fall in one place or another on a school. So schools are as one might expect, thoroughly confused about how to deal with this technology.
Some of you haven't seen 3D printing yet and may not get this, so I hope the rest of you will forgive me while I do a favor to those people. As Scott pointed out, there are a number of different techniques, but if you don't know what a 3D printer looks like or does, first of all, there are some upstairs, but second of all, it may be helpful to know that at least one of the techniques, and the technique that shows up in the $1,000 machines, is basically a glue gun that goes back and forth on a very simple platform, laying down very thin threads of hot glue, which harden, and layer by layer, it then builds up a complicated process like this, a complicated object like this. And there are other techniques, but that's at least one way in which you can wrap your head around the idea that just as we've gotten used to 2D printers, which put ink onto paper, we are all about to get used to any number of 3D printers, at least one of which you now understand.
Now that you understand it further, I want to ask to the panel, why has this come about? What do we need in design? What do we need in our world? What is it that 3D printing is offering us?
Well, in the medical field and biomedical research, we think that 3D printing, we focus on a few different things. One is models that help researchers and physicians, surgeons, patients, students understand the complicated concepts that they're talking about. For example, there on the table, you see a 3D printed heart in white. That actually helps some surgeons detect, and we can actually start maybe passing some of the models around at least. That's fine with me if you want to pass them around and get a feel for what they look like. And here I'll start passing the skull around too. So it's a surgical planning tool. It's a communications tool. It's an educational tool. It's a way to create objects that you can't create in any other way, like maybe that protein model over there. It's a way to make custom objects that otherwise you don't want to make a million G.I. Joes. You want the G.I. Joe with your face on it, maybe. Or whatever, or Barbie, right? Whatever it might be, right? The idea is to use the 3D printing to create things that you can't do any other way.
And to add on to that, it's also about customization too. You know, you can customize it to your lifestyle, to your body type, to your favorite color. You know, you can really it's all about customization. And a lot of brilliant people are out there who, you know, I feel like one of the hurdles with 3D printing is the design aspect, because not all of us are designers. I mean, some of us just don't have that skill, right? But there are a lot of people who are willing to help out and to teach you, and open source forums like his. It's just the ability to design and print is out there for you. Yeah.
Yeah, there are a couple sweet spots with 3D printing. One of them certainly is customization, and the medical world loves that because every body is morphologically different, so therefore it completely rationalizes it. But then you have companies like General Electric and the SpaceX building rocket parts. They don't care about customization. What they care about is complexity. They're able to take very, very complex geometry and instantiate it very rapidly. So that means that they can take, for example, 20 parts that might comprise a complex rocket engine and essentially print them out of Inconel and superalloy, and it's now one part. That means you have less points of failure, less weight. Everything about it is more efficient, simpler, faster. GE is doing this with turbine blades now. They're able to make a turbine blade that would be unmakeable a couple years ago because it allows complexity, because you're going directly from digital product or digital file into a physical item. So complexity is the other one. The other one is immediacy, that you can get a lot of shots on goal. So if you're a startup company with an idea and you're trying to get to market fast and wary of your burn rate, you can get a lot of parts out there in a hurry, try them out on the market. Once they succeed, yeah, then you can go off to China and make your injection molds and mass produce them. But this gives you a lot of buffer against the kind of market demands that a startup would typically face. So those are a couple of the real sweet spots is customization one, complexity is another, and immediacy is the third. So those are, if you have a business model that really invites those, this is really what makes that happen.
I guess I would add that it has the potential, in some cases at least, to really change the way you go from an idea for a thing to a thing that you can feel and experience and test. And it allows a potentially new way of going from a testable thing to a distributed thing. Instead of shipping objects, you can ship the files and have them show up in many, many places, and by the way, then be modified.
Just very quickly, one of my colleagues likens it to a vacuum cleaner, right? If your vacuum cleaner breaks and you need a part, well, you have to go to Sears or whatever and get your part and pay for it. And of course, they have to stock it, and there has to be a warehouse for it, and you have to make it. Where instead, if all you have to do is say, okay, my vacuum is broken, here's the part. You contact the manufacturer and say, okay, here's the file. You get the file, you go and you print it maybe on 3D hubs, and your vacuum works today instead of 3 weeks from today.
Just to add on. 3D hubs, just add on to that. They've partnered with a company called Fairphone. I was new to it. I guess it's this popular phone company in Europe somewhere. But anyways, Fairphone partnered up with 3D hubs where you can, if you want a Fairphone case, you can get it printed through 3D hubs and then pick it up at your neighbor's spot. So it's the same idea as, on-demand local manufacturing quickly, the next day.
I want to go further into the design realm and really push them because I'm a designer and we will also gladly take questions, right? So further into the design realm, maybe reinforcing what this term rapid prototyping means. I know we're already now touching on it, but to go back to the idea of we're talking about the output, what comes out of the machine, what we can make, let's talk about the input. Where do we start? When it comes to rapid prototyping, this idea of iterative design, families of solutions, Jon and I talked about earlier, maybe we could go into the design side more heavily and speak to some of those aspects of whether we're modeling from scratch, whether we're scanning something in, how that process flows.
I can talk briefly about a program called Tinkercad. Everyone should look up Tinkercad. It's like one of the best programs out there. You can basically click a button that looks like a cube, and it comes on there, and then you can adjust the cube to make it higher, lower, flatter, change it to purple, I don't know, whatever you want to do. Press print, and it'll print. I mean, that's that easy. It's a few clicks of a button. So definitely look into Tinkercad. Everyone is a designer on that site, for sure. I'm sure you
Okay, what you can print is actually coming from a lot of different areas, and that's expanding as well. So the entry-level person who opens up a machine, they can actually download stuff from any number of download sites and print something within minutes. And you can, if you want, you can print a gun that way. You can print all kinds of stuff that way. There are hundreds of thousands of parts. 99% of them are thoroughly worthless, but they are there to be had. And you can find, your doorknobs and your whatnot that way. So that's your entry level. You get to the next level and you go to somewhere like Shapeways, which is a site worth checking out, and you can download a part and then you can also modify it. So you download that drawer pull, and now you can modify some of the attributes of it that the designer has spec'd that you are now able to modify, and you can print it out that way. So that's kind of the next step up. Beyond that is something like Tinkercad, where you're getting into a CAD modeler. And then there are also full-blown template-based modelers, and that's one of the things we're working at 3D Systems, so that you don't have to have technical skills to model something. You can download the template, and that template invites you to change things at will. We saw that in the video, and that was actually a very good description of it, where it's kind of like configuring a car online. You configure it, and then you go and pick it up, and it prices it and everything like that. If you really don't want to go full bore, you can learn CAD. And CAD comes in a lot of different varieties. There are solid modelers, surface modelers, tessellation modelers, functional representational modelers. And the important thing to know about there is you really have to design and understand what your intent is before you make the CAD leap. One of the things that we discovered, I dove into Scoliosis Brace here, and I have a modeler that I use called Pro Engineer. It's a very, very powerful thing. You can design 747s on it. However, it gets ground to the floor when you try to design something like that, because you have a certain type of geometry that is not in the sweet spot of a solid modeler. That's in the sweet spot of a tessellation modeler, and I didn't know it when I started it. So I was going a hard route. Then again, if you have a tessellation modeler and you want to do a 747, forget it, never happened. So you really have to understand what it is that you're modeling, find out who else is using, find out what the types of apps that other people are using to get there. Medical, amorphous, cinema, Hollywood, automotive, every industry, every application has a modeler or two that are perfect for it. But no one modeler is perfect for everything at all. So caveat emptor.
One other input technique which hasn't been mentioned is coming onto the market right now at the consumer level is the equivalent of the printer, scanner, faxer machine. A device with a turntable, you put an object on it, the object rotates on the turntable, it creates a scan, and the same machine can then print another copy of this, or for that matter, send the file elsewhere. Under the hood, all of these things they were just talking about are happening. But over the hood, it's a transporter device.
Another way to model is directly from scanned data. You may have seen up at the 3D print zone up there that they have a few folks are there with scanners. So the idea is you take and you collect three-dimensional data the same way that maybe your Xbox Connect uses and interprets 3D data. There's lots of ways to get that 3D scans into the computer, and then of course you have to massage them, and there are programs to do that. The other way to do it is again, this protein or the skull that's going around, that was all collected from data that was inherently 3D to begin with. So a medical image stack or points in space. And then there are there are open source programs out there that anybody can download and use to take that 3D data, put it into a format that's compatible with a 3D printer, export it and share it and print it, whatever.
If we could still go further into the idea of iterating when we design, perhaps I'm thinking of some of Jon's work with talking about maybe the existence of how many files of hands there are, how many families of solutions that have grown in however long, of time, if you could speak to that, and then maybe perhaps some more of Scott's in-depth work with design and aesthetics and how iterating 3D printer.
I told Monika, and I failed to send you the slide, I'm sorry, that a few months ago I made an evolutionary tree that showed how the original 3D printed design that I saw on a YouTube video has proliferated in our group into about 20 different variations. There's the cyborg beast, and there's the talon hand, and those have two different sets of properties, and other people have brought those together, so there's now a talon beast, and there's an Odie hand, and these things mix, match, recombine, and evolve, really, in this gene pool, which is the ongoing community. And so it goes beyond actually being a single design process with the designer. It's very much a cultural evolutionary process in which these things are proliferating through the efforts of many people and many ideas mixing and matching and recombining like genes in a gene pool.
So one of the great attributes about 3D printing is that complexity is free. You know, that's kind of the subtext that goes along with it. And
that's a really important concept. And
I'll say it again, complexity is free.
And what that means is that a 3D printer is as happy printing, it's no harder for a printer to make a cube than it is to make a really complicated machine.
More often than not, actually, the complicated thing will be less expensive and easier because it's less mass. You pay literally by the mass. And so what that means for the industrial designer is that if we want to infuse our parts with something beyond simply the utilitarian mechanical functionality, we can do that at no extra burden of cost to the process. So one of the reasons, or one of the things we found that made that a sweet spot was looking at scoliosis bracing here, and there's an early prototype there. Now scoliosis is lateral curvature of the spine. It works when the girl, it's 90% girls, wears the brace 20 to 22 hours a day, 2 to 4 years. The reason it doesn't work is 87% of the time because she doesn't wear the brace the prescribed amount. Okay, that means that the miserable brace, which is the standard accepted medical brace, is not comfortable, and it's insulting and demeaning and miserable for the girl in every possible way. So that means all of a sudden, well, we have to make it a fashion device that happens to have a medical component instead of a medical device that gets dolled up. So we looked at that. We created a process of 3D scanning, correcting all this stuff, and 3D printing the brace. Now what we get out of that is we can create this lattice pattern, and we've evolved the lattice pattern. We've got all kinds of fenestrations. What that means to the patient is, for one thing, it makes the pattern, which is highly complex and highly data intensive, it makes it lighter weight physically. It makes her skin breathe, so she's comfortable wearing it, so she'll wear it more. It means that we can have it absolutely discreet under clothing, so a simple t-shirt hides it. And it means she gets to choose the pattern from a library of 10 or however many patterns. What that means is she has agency in the design process, which means she has more of an emotional attachment to the product, which means, again, she'll wear it more. And so that's all we're attacking here, is we're attacking her unwillingness to wear the brace by sweetening the taste of the medicine. And that is entirely enabled by 3D printing, because you can create the kind of attributes that are going to skew the compliance variable into the favor of the medicine. So we're doing it with that. We're doing it with prosthetic limbs of all kinds. We're doing it with wrist-hand braces, which you see upstairs. All of those things where additional complexity that comes for free with 3D printing, free or usually actually reduced cost to the final part, that actually improves your medical outcomes simultaneously. So there's multiple dividends to be had because of the attributes unique to 3D printing.
So I have actually invited a guest to field a question, a local here whose work I just recently came across, but I think it builds on what we're talking about to, in this case, entice somebody to wear a brace. Here someone has, we can see the slide correctly, sort of an aesthetic enhancement to prosthetics here. So this is Evan. Evan, if you would even introduce yourself for a minute, too, would be great.
I'm a student at the California College of Arts studying for my master's degree in architecture, and I decided to apply those skills to another field and see what I could come up with. And my question is, how could the patterns, like on the scoliosis brace here, could those patterns be intricate to the design itself rather than just applied on the surface? Like, could they determine where it bends and how it flexes and everything like that, but not only just from a mechanical side, like on that wrist brace it's just vertical lines? Could they be more complex and intricate patterns that provide the same thing?
That's a great question. I didn't put you together with the picture a second ago. That picture went around 3D Systems internally, and then it ended up in my inbox, and I just responded, reply all, let's hire them. And so, you got a job, you're good. Come on over. And that's actually a very astute question, because since complexity is free, you can not only add the aesthetic attributes that you like, but all kinds of mechanical attributes. So we have something that we coined selective flexure, which means that if you compromise a structure in a certain axis, it will bend a certain way and not another way. So the fracture brace, the black fracture brace you see there, will bend open like a taco, but it can't bend torsionally, which would undermine the efficacy of it as a fracture stabilization brace. But looking ahead, and this is where things get exciting with 3D printing, we're getting into this world now of what we call digital materials. And that is an entirely new thing. That is a break in the continuum of fabrication of anything, because now you can print simultaneously polymer and elastomer in a dithered way. So for example, you can have something that is as squishy as a gummy bear imagine a ruler, as squishy as a gummy bear on one end and as hard as solid plastic on the other, with a linear gradient between the two. Impossible any other way. Or a nonlinear gradient. Or you can have that Scoliosis brace, for example, have parts of it that are shore 7 and others that are shore 60. And you can dither evenly between them. So that's what we're getting into now, is these very interestingly biomimetic materials by mixing different materials simultaneously in a dithered fashion. And the dithering happens at a micro level, so you can't detect it, but you can change all of the mechanical attributes in any location of your part. So the sky's really open as far as all the ways you can mechanically change, compromise, or very deliberately affect mechanical attributes of a physical artifact now.
I was just going to say, we have a case knocking about in our community right now of a flexi hand, it's called, made out of a flexible filament material called Ninja Flex or Filaflex. But in this case, it is a single print. That hand that's going around has got hinges and all sorts of parts. This is one piece. But it's got little wedges cut into the knuckles and into the shape of the palm, so that when the cords cause it to contract, the fingers curl and the palm wraps and you get a really interesting grip. So that's an example of that kind of thing, where you're using it to determine the angle of the various bends. They act as springs to open the hand back up, and they provide actually a more biological feel as well.
Oh, thanks, Evan. When you say complexity is free, that is a true principle about the process of 3D printing. But it can be misleading when we talk about that complexity is free as a blanket statement, because creating these more complicated materials or complicated designs like Evan's talking about or whatever, that does require a designer, right? And the more complex the design, usually the more time it takes to create that design. And I think we're seeing this a lot actually in a lot of different fields, that it's easy, for example, to sequence genomic data. Just to go off on a tangent for a second, getting genomic data is very easy. You get tons of it. It takes less than a week, but it takes more than a month to analyze it by a highly skilled bioinformatician. It's the same thing, I think, for a lot of this 3D design, right? That's actually the benefit of repositories like mine that allow anybody to take advantage of the design skills of a smaller community of designers, the same way that Jon is doing with the hand. So in one sense, yes, complexity is free for printing, but it still does take the design, maybe getting back to what your question is about the design, yeah, it does take some effort.
And actually, while you have the mic, I wanted to go into a little bit more of your work, and we've all heard he's expert in computational biology. So first, I'd like to hear more about that in reference to the projections and even current happenings now with 3D printing. It's not just plastics and products, but we're now talking about biological printing and even the printing using stem cells for organs. So maybe if we can even, loft some things out there and have everyone understand where this is and where this is going.
Okay, well, bioprinting is kind of a separate field in the 3D printing world. And I don't know if we've talked about the Gartner hype cycle that was mentioned earlier today in the plenary session, I think, about how there's an initial phase of hype, and then the trough of disillusionment, and then finally when things start to become useful. So, for example, smartphones went through that hype cycle. And some things go through that hype cycle faster than others. 3D printing actually stayed just before the peak of the hype for years and years on the Gartner hype cycle. And then all of a sudden, bioprinting showed up right at the very beginning. 3D printing stayed where it was, but bioprinting started zooming up that slope very quickly. So bioprinting is very exciting, but there are a few. And so let me tell you about just one application is for high-throughput screening using cells. Instead of in vitro or in vivo techniques, you can actually print tissue, like liver tissue, and then do your high-throughput screening on liver tissue, for example. There's a company doing this called Organovo, partnered with the NIH. And that's great, except the tissue that we're talking about is maybe 1 millimeter square. Okay? So actually printing a functioning organ, yeah, you can put together a bunch of cells that look like a liver or a kidney or whatever, but getting a functioning one is more complicated. And so there are actually other folks like Jordan Miller at Rice University who's putting together ways to create vasculature using stem cell technology and printing in sugar to create filaments around which eventually you grow stem cells, create vasculature, which can then be incorporated into a larger design for an organ. But that is, in my opinion, probably at least 10 years out, even though people are bioprinting today.
Shy of bioprinting, though, there are tremendous dividends that are being reaped right now every day from the combination of 3D printing, 3D scanning, and biological need. A lot of people don't know it, but Invisalign, which replaced the miserable hellish braces that we all grew up with, that multi-billion-dollar industry in 5 years or so, that is an entirely 3D printed industry. That they do the intraoral scan, they do a digital interpolation from where your teeth are now to where they want to be, and then they print everything, and we print 17.8 million individualized units per year of those. 17 million is very, very high volume production, and is completely rearranged orthodontistry. Same thing that went on with hearing aids. Acetabular hip cups, if you need a hip replacement, knee replacement, all kinds of different bone replacements. They print it in a trabecular lattice structure that promotes bone ingrowth, so it actually promotes very effective osseointegration. They're printing out of titanium, 17.4 stainless, all the biocompatible metals. Gaining a lot of traction now is PEEK and PEK, PEEK and PEKK, which are also biocompatible polymers. And so we're seeing a lot of those for implants now. So even though we aren't printing our kidneys and livers yet, there are plenty of solutions all up and down the body that actually are being 3D printed for very significant solutions.
Okay.
Yeah. You can see that in the skull, the titanium insert right there. There it is. That's an actual implant that is used. That was actually a soldier returning from Iraq, had terrible wounds, and he was able to get a normal-looking head again because of a titanium implant.
So the time calls for us to move to panel 2. And if you do have a question, I'll try to take at the very end because there's a chance that it may be answered by the next panel, so we won't take it now. But everyone will be around, and we're informal enough that we can have people join in the conversation for panel 2 as well. Yeah? Okay. So Joel.
Thanks very much.
Thank you.